Today we are going to study example of linear programming. So first example of linear programming is in front of you on this slide. Vitamin A and B are found in food F and F2. So there are two vitamins, vitamin A and vitamin B, and there are two types of vitamin A and B and two types of food, F1 and F2. One unit of F1 contains 3 units of vitamin A and 4 units of vitamin B. Okay, that we can write that data in tabular form below that example. So 1 unit of F1 contain 3 units of A and 4 units of B. So in front of F1 I have written 3, and in front of uh, in B vitamin I have written 4. Okay, 1 unit of F2. So in second row I have written F2, which contains 6 units of vitamin A. So I am writing in A column 6 and 3 units of vitamin B, right? One unit of F1 and 1 unit of F2 cost 4 and 5. So in front of 4, in front of F1, I'm writing 4, and in front of F2 in cost third column, I'm writing 5. Okay, the minimum daily requirement of a person of vitamin A and B is 80. So in the third row, I am writing minimum requirement, which is 80, and for A and 100 for B vitamin. Assuming that anything in excess of the daily minimum requirement of vitamin A and B is not harmful. If something is excessive, that is not harmful. It should not be minimum than 80 and 100 for A and B respectively. Find out the optimum mixture of food F1 and F2 at the minimum cost, which meets the daily requirement of vitamin A and B. Okay, formulate this as a LPP. So we do not have to solve the problem. We just have to formulate linear equation. So we want minimum of vitamin A 80 and minimum of vitamin B at least 100. Okay. So we are going to solve this problem. The problem is to find the quantities of F1 and F2 so as to meet the daily minimum requirement of vitamin A and B at minimum cost. So problem is for the cost minimization. So decision variables, there are unknowns to be found out here. Okay. So X1, we consider X1. We want F1 and F2 quantities. Okay. So we assume X1 as F1 quantity. So X1, let X1 is equal to the quantity number of units of F1 required to meet 80 vitamin A daily requirement and 100 vitamin B requirement. And X2 quantity, X2, we assume that quantity or number of units of F2 which is required to fulfill 80 units of vitamin A and 100 units of vitamin B. So that is decision variables X1 and X2. We define for the quantities of F1 and F2 to form a linear equation. Now objective is to minimize the cost of the food. Now the cost of the X1 units of F1 is X1 into per unit cost. This is 4X1. Okay. So at the third column, if you see there is a cost. So if we consider X1 is the quantity of F1, so 4X1 will be the price because the 4 into quantity is the requirement of F1. Similarly, cost of X2 units of food F2 is 5X2 because 5 is the cost of the unit and X2 is the requirement of units of F2. Hence, the total cost is 4X1 plus 5X2 is equal to C, say cost. Hence, the objective function is to minimize the cost. So C is equal to 4x1 plus 5x2. Now we have found out the optimum function. Okay, what we want to achieve. It is objective. Now we want to find out the limitation constraint. First constraint is minimum requirement of A is 80 units. Okay. Minimum requirement of A is 80 units. The number of units of vitamin A contained in x1 units of food F1 are x1 into number of units of A contained in 1 unit of F1, that is 3x1. So if we similarly number of units of A contain x2, units of F2 will be CX2, 6x2. So the total intake of vitamin A will be 3x1 plus 6x2, which must be at least 80 units. So 3x1 plus 6x2 is more than or equal to 80. That is vitamin A constraint. So if you see the table. In table, you will see F1 how much required. 3 units required. 3 units of vitamin A required for F1. 6 units of vitamin A required for F2. So F1 quantity what we have assumed is X1. So 3x1 will be there, and we want six units of vitamin A is available in F2, but quantity of F2 required is X2. So 6x2 it will be. It will be 6x2. So if you see the column, second column, there we required F1 3 units and F2 6 units. So F1 quantity is X1. So 3x1 plus F2 quantity is X2. So 3x1 plus 6x2 is should be equal to 80. That is minimum requirement at the third row, or it should be more than 80. At least 80 we want. Similarly, if you go to third column, that is B column for the vitamin, so it will be 4x1 plus 3x2 equal to 100, or it should be more than 100. Okay, so we got equations. We got two equations. 3x1 plus 3x1 plus 6x2 should be equal to 80 or more than 80, which is vitamin A necessity or requirement. Minimum that much is required, and we have written how much we are getting from the F1 food and how much we are getting from the F2 food, and we have total it to 80. Similarly, for the vitamin B, 4x1 plus 3x2 equal to 100 or more than 100, which is B vitamin limitation or the constraint. Since the number of units of x1 and x2 cannot be negative, so x1 and x2 is equal to 0 or more than equal to 0. So it will not be minus. It will be either no vitamin A or no vitamin B, or plus 1 vitamin A, 1 mg vitamin A, or 2 mg vitamin B, like that. So it cannot be negative. So x1 equal to 0 or more than 0, and x2 equal to 0 or more than 0. So that is non-negativity condition. So we can write the it in format where our optimum function is 4x1 plus 5x2. That is 4 is the price of F1 food, and x1 is the quantity of F1 food, plus 5 is the uh, price of the F2 food, and x2 is the quantity of x2 food. So 4x1 plus 5x2 we have to minimize. That is our main optimum equation, objective equation. And constraint equations are 3x1 plus 6x2 is equal to 80 or more than 80. Vitamin A constraint. Vitamin B constraint is 4x1 plus 3x2 equal to or more than 100. And non-negativity condition is x1 should be equal to or more than 0, or x2 equal to or more than 0. So next example we will see in the next lecture.